Then do like
Good.
no sign modification.
Okay, so let's talk about number 9 and make sure everybody's kind of got a feel for what's happening on number 9.
What'd you say?
So here's this block, right? We can model it just like this, all right? So we're pulling it along like this, bless you. So we're pulling it along like this. So obviously, if you just start with the block, okay, you've got, oh, all right, we got gravity pulling down, we've got the table pushing up, so we have those two, right? Cool. Bless you.
Thank you.
Now, how do you know that there is friction acting on the block?
You didn't say it was a frictionless surface.
Huh?
You didn't say it was a frictionless surface.
Well, number one, I didn't say that. That's true. But also, just by virtue of the fact that I have to apply a force to pull it, means that there's friction. Okay? All right, so I got some force friction going this way. Now, because you're at a constant velocity, what do you know about this horizontal force over here relative to that force friction?
It's the same.
The same, right? And so that's that 462 newtons. So this is your force X, 462 newtons. Now, but we're not just like dragging it like this, okay? We're walking upright and we're dragging it like this, okay? So there's still gravity pulling down. There's still the normal force. There's still friction. There's this. But now, because we're pulling it like this, now we have this tension coming up like this, right? Now, think of this as just being a triangle. This tension represents the hypotenuse of that triangle, right? This is a 56-degree angle, and this is 462 newtons, okay?
Do you
Good
not
so
put it
far.
from the center?
Huh?
Do you not put the line from the center?
Yeah, it doesn't make any difference. Yeah, it's just, as long as it's just, if you want to go back and sort it like that, it just doesn't, I'm not going to be that picky about it. But if you consider this being a triangle, well, triangles have 3 sides. So here's your horizontal component. There's your tension, so that means there's going to be a vertical component here. So just come in here, draw a line up here, call that like Fy, something like that. Yes?
I did the vertical component on top of the force normal.
That's fine, it'll work, that works there too. Right? It's just a little bit easier to see if you draw it there, it doesn't, as long as it's there, that's all that matters. Okay? So, so on B, you want to find this tension. So, from a geometry standpoint, you're finding the hypotenuse. Kara, what do you know, Kara, I was off by an 8. Kara, what do you know about the hypotenuse of a triangle relative to the other 2 sides? Yeah, so you know when you find that tension, that has to be bigger than the 462. In my defense, a former student of mine named Kara just donated like 20 bucks to the hair fund. That's why I had that on the mind. So, anyway, so you know that answer has to be bigger than 462, because it's the hypotenuse of the triangle, okay? So, you're at 462, but remember, when you're doing work calculations, you only consider the force that's in the direction of motion, okay? That's the only force that you consider. So, anyway, make sure on number 12 that you have given like a formula at the end of each one. Let me give you a hint what I don't want on number 12. Do not just say, oh, F equals ma, okay? F equals ma is not a valid justification. Now, you could say, oh, with the smaller mass, you get a bigger acceleration. Yeah, that's cool, you can say that. But just because something has a bigger acceleration doesn't mean that it's going faster. That doesn't mean that it's going farther, okay? You have to give some other like kinematic equation to justify that. Yeah, you can say, hey, yeah, there's a bigger acceleration, but there's that equation, or distance equals 1/2 at squared plus v naught time, okay? So just saying it has a larger acceleration is not a justification for saying, oh, it's going to go further, okay? Keep in mind the time is going to be the same, okay? That's gonna be another key component of this. Keep in mind, the time is gonna be the same. Basically,
Can we use D equals VT?
huh?
Can we use D equals VT?
No,
Or,
because it's accelerating. What's the only time you can use distance equals velocity times time? When you have a constant velocity. Guess what? It's not constant. Now, you can use like momentum. You can say momentum is mass times velocity. So if they have the same momentum, smaller mass has to have a larger velocity. You can do that route, okay? But you can't use distance equals VT. You should have a few negative answers on this assignment, okay? Not very many, but some of them should be negative.
I only got 2.
Your answer to number 11 would make a horrible, not horrible, but a not very good GPA,
Me too.
okay? A not so good GPA. Your answer to number 10 should be something times 10 to the 4th. And your answer to number 8A should be something times 10 to the 5th. So remember on that 8A with the bucket, you have to lift two things. You have to lift the bucket itself, okay? And that's already in newtons. You don't have to do anything with that. I already gave you the weight of the bucket. That's in newtons. Don't have to do anything. But you've got the volume of the dirt, and density is mass divided by volume. So I gave you the density and I gave you the volume. So you can multiply those two numbers together to get the mass of the dirt. Then take the mass of the dirt times G, that's going to get you the weight of the dirt. Add those two numbers together, the bucket plus the dirt, multiply that by the height. There's the work that you're going to do. Okay? Well, good.
11.
What about it?
Just as I understand.
Okay. So, what are the two most important words on number 11, Mason?
Down and constant velocity.
That's right. So, what's the force that's making it go down the inclined plane? But what component of gravity? What component of gravity? Normal or parallel?
Parallel.
Yeah. So if you can find your force parallel, which is Fg sine theta, which direction is your frictional force going to act?
Against that.
Yeah. So if you're at a constant velocity, what do you know about this force parallel relative to that force friction?
Pretty equal.
Yeah.
So you just find the force parallel.
Yeah. Then multiply that by the length, there's your work.
Okay.
Okay? Because those are the only two forces in pound. There's no external pushes or pulls or anything like that. Okay.
For 12A.
Anything else?
You have to go around, like, I did this.
Good, Zoe?
Yeah, you know,
Okay.
it's over time, so you
Oh, seriously?
So does the length matter?
there's no equation that specific time. So you have to choose one.
How do you calculate work?
Oh, that's gonna work with me.
Yeah.
My bad.
Yeah, it's
What? Tell me that's, tell me your question is better than that.
I hope so. I mean,
I was like,
it says on number 9, when you ask what work is done by the friction, isn't it like friction's in the opposite direction of the motion?
Yeah,
So would it just be the
Oh wait! Oh my god!
Is that even
I know what I
considered work?
did.
yeah, because that's generated heat.
uh,
It's work done in overcoming that friction force. Just like when you push your hands together, you do work in one direction, friction
Yeah, I
is generating
multiplied
heat in
it
the
because
opposite.
the forces.
We're talking about force.
If, now what?
just in that case, like the friction doesn't have to be in the direction of
No, friction's always in the opposite direction of motion. So, any work in the opposite direction of motion is negative. Any work in the forward direction is positive. So you're pulling it like this, so that's that 462. So you're doing positive work in pulling it, but there's negative work in the opposite direction. And that's how much thermal energy you use.
You know 2 things, that's all you need to
Okay, anything else?
I should have already known this.
Yeah. Ah, what was that? Ah!
I don't know.
Like this cat versus like cross with dog. Ah!
I don't know.
Okay. Well, if you need anything else, let me know, dear. Okay, going once, going twice, sold. Get that handed in. Hey, don't flip out, these election notes got handed out.
Fair. So either way, move it around just like any other equation. If you multiply these 460. Or wait, I'm sorry. Yes.
Okay, so what number did you get?
Nice. No, so like, it's time the same acceleration, so it cancels out.
Yeah, and you multiply by h. Yeah, exactly. And then you'll divide by the thing, and that'll get you the answer.
Or just 1, 2, 0. 90.
Make sure that you're using the horizontal component, not what multiplication we just had.
Wait. What?
We're using the horizontal component for 462
Wait, why not the tension though?
because work only happens in the force. Yes. Same.
Okay, let's try it again. 6699?
Well,
Except around 671. Yeah, to the third. Yeah, one more time.
I know you guys. Oh my god. Negative signs, the next one's the exception.
Wait, what are we getting negative on?
Next week.
On 90? Did you still have one negative?
I mean, I did, but you don't really have to.
Is it fingers?
No, my highlighter.
So I think you were like,
No, that was her.
I don't want you to just pull it.
Yeah, the changing, make sure the changing words make a change.
11?
Okay.
No. No, because 11 is
Yes. Yes. Because you're going down.
And like the reason that you.
Anytime.
No. Okay.
No, it's because there's acceleration on both sides, so it turns around that side.
Are we going?
Yep,
Okay.
I never stopped it, so,
I guess we're still doing that.
yep.
Okay, so here's the deal. So here's the last of the really, really big topics. It'll take us about a week to get through all of this. And this is this concept of energy. And so what you'll see is that energy ties together some of the things we've already talked about. Like we'll tie it back into Kepler's laws of planetary motion. We'll talk about work, we'll talk about force, we'll talk about distance. So a whole bunch of things that we've talked about are all going to kind of get rolled into this idea. So when you talk about energy, everybody has a sense of what it is. So like when you all walk in, I can get a pretty good sense of just how much energy that you have, right? Now some of you are pretty steady on your energy levels, okay? You know, some, there's more variance. Like hip's always pretty cool, right? It's just sudden, you know, okay, right? Pretty cool, right? Hannah's a little bit of variance, okay? Paige, usually kind of upbeat, right? Okay, Kira's like, ah, okay? So, I can get a feel when you all walk in the door how much energy that you have. You guys get a feel for how much energy you I have. Like, oh, poor Camp's on his second can of Coke today. Wow, caffeine's really kicked in, okay? Okay? Or maybe, hey, poor Camp's not feeling a little well today. Maybe he's a little bit more laid back. But if I said, write a definition of energy, what would you say?
Keep stuff going.
Keep stuff going. Okay? Now, to keep stuff going, what do you have to apply?
Force.
A force, unless it's a friction of the surface, right? Okay? So, we're gonna keep going with this thought. So if you apply a force over a distance, what are you doing? Work, okay? So from a physics perspective, energy is the capacity to do work, okay? It's a simple definition. So if you have energy, you have the capacity to do work. Now, if you think about it, Saturday morning, 8 o'clock, Aunt Martha's coming over for breakfast. House needs to be vacuumed. Mom says, hey, need you to run the vacuum cleaner. Okay. And if you say, Mom, and if you pause for dramatic flair, this helps, and you go, I just don't have the energy. So from a physics perspective, what you're telling your mom is that you do not have the capacity to exert a force over a distance to run the vacuum cleaner. Okay? That's what you're telling your mom. Okay? I do not have the capacity to exert a force over a distance. Okay, that's it. And they're right. It's like, man, I just don't have the energy. I can't push it. And your mom's gonna go, you're young, get out of bed. You have the energy. Find it somewhere. Okay? So, but that's kind of a working idea. And if you think about that, when somebody walks in, like, wow, they're really high strung, right? They have a lot of energy. They have a lot of capacity to do work. Okay? If someone's pretty lethargic, wow, you're not going to get a lot of work done today. Yeah, just kind of chill out, right? So you get a feel for how that's going to play out. Now, we're going to have two broad classifications of energy, kinetic and potential. Kinetic comes from the Greek word meaning kinesis, which means motion, okay? So kinetic energy is going to be something that's in motion. So you can have KT, which stands for translational kinetic energy. So that's like if I just take this tennis ball and I just throw it up in the air, okay? So that's going to be translational kinetic energy. You can have rotational kinetic energy. So if I take this tennis ball and I make it spin, then it has rotational kinetic energy because this is going to be I, and I is going to stand for what? Moment of inertia. Omega is going to be,
Oh, that's a
huh? Yeah, how fast you spin. So if you look at these two equations, this is mass, measure of inertia. This is I, moment of inertia. This is how fast you're spinning. This is, or how fast you're moving. This is how fast you're spinning. So you're multiplying the two similar quantities together. On your kinetic energy, do you think kinetic energy is a vector quantity or a scalar quantity? Vector, why?
Because velocity is vector.
It's true.
And it can be.
So let's look at it. Hold that thought. You hold that thought. Okay? So I throw this tennis ball up in the air. Is the kinetic energy changing? Yes. Why?
speeding up or something.
Yeah, I'm changing my velocity, right? So on the way up, it's going to have a positive velocity. True? But on the way down, the velocity is going to be negative. But I'm squaring that velocity. So even if you have a negative velocity, you're still going to have positive kinetic energy. So all forms of energy are scalar quantities because of the fact that we can never make them negative. Okay? Because that's v squared. Even if you have like negative angular velocity, you're still going to end up with positive rotational kinetic energy. Okay? mgh, mass g, how high you are above the ground. This is the energy stored in the spring. This is a spring constant. This is how far you can
Is that a
press the
K
spring.
or?
Yeah, that's a K. It's 1/2 kx squared. So with that one, if I take this, talk about UG, oh, that's just mgh, all right? It's a product of the mass, your gravitational acceleration, and how high you lift it. So if you look at that spring constant, so if I take this spring and I pull this down to a notch, first off, when I push that down, did I do work?
Yes.
Yes, why?
You moved it in direction.
Yeah, I exerted a force over a distance, right? If I throw this ball up in the air, do I have to do work on it to throw it? Yeah, okay. Gravity is doing work on it because gravity is making it slow down and speed up. So gravity is doing work. There's a whole bunch of things that are doing work, and what you'll see is that work is also equal to the change in your energy. So when you look at these values, the energies themselves will always be positive values. But energy, Mother Nature doesn't like potential energy. Somehow or another they got crossways with each other. Okay, not sure what happened. I don't know if it was a TikTok video, Snapchat, I don't know. Somebody said something somewhere, somehow, Mother Nature doesn't like potential energy. And here's how you know that. If I let go of this ball, what's it going to do? It's going to fall. But now, if Mother Nature liked potential energy, what would the ball do? The ball would stay there. But if Mother Nature liked potential energy, I would let go of the ball and it would stay. Mother Nature goes, I like kinetic energy better. That's the chosen one. We're going to make that ball move. Same thing is true when I do work and I store the energy in the spring. So obviously the farther I pull it down, the more I compress the spring, the more potential energy that I'm going to store. So when I release this lever, what's going to happen? Mother Nature doesn't like potential energy. She's going to change that into ball's going to get launched, right? Okay. So I took the potential energy that I stored in the spring and changed that into the kinetic energy of the ball, and then it started moving, and then it's going to change into gravitational potential energy, and Mother Nature doesn't like that, so Mother Nature goes, I want you to come back down because I like kinetic energy better. And clearly, if I pull this thing all the way down to the bottom and let go of it, okay? So I stored a lot of potential energy, so that's going to create a lot of kinetic energy, which would create a lot of potential energy as it gets shot up. Okay, so that's the broad idea. So if you look at the units of energy, so let's look at 1/2 mv squared, right? So that's going to be kilograms times meters per second. And that whole thing is going to get squared. So I get kilograms meters squared over second squared. If you look at MGH, that's kilograms times meters per second squared times meters. You also get kilograms meters squared over second squared.
Second squared on the bottom.
Yeah, because you're squaring that whole quantity of meters per second. So it becomes meters squared over second squared.
Oh, okay, yeah. I was talking about like the second one you were after.
No, yeah, I marked, I wrote that, didn't mean to.
Okay.
There. Okay? And then if you look at moment of inertia, 1/2 I omega squared. Well, remember I is kilograms meters squared. Omega is radians per second, but that's going to get squared. So we still end up with kilograms meters squared over second squared. So then if you look at work, work, that's force times distance. Force is kilograms meters per second squared times meters. You still, oddly enough, get kilograms meters squared over second squared. What?
For I butt. After kilograms meters squared.
Times radians per second quantity squared.
Okay.
Now, if you look at Einstein's equation, Einstein's most famous equation is E equals mc squared. Okay? Well, look at the units. You have kilograms. Anybody know what C is?
Speed of light?
Speed of light. Okay? Speed of light. That's in meters per second. That's going to get squared. So oddly enough, you get kilograms meters squared over second squared. So Einstein's equation had to be E equals mc squared. It couldn't be E equals mc. Because if Einstein just multiplied mass by velocity, what would you get? What's mass times velocity? In seconds, otherwise known as, rhymes with momentum. Momentum. Okay? So Einstein couldn't say, E equals mc, because all the other physicists in the world go, you're a schmuck. Okay? You don't get energy, you get momentum. Okay? So The beauty of what Einstein did is he was able to realize that there wasn't anything in front of it. Okay, there wasn't 1/2, it wasn't a fourth, it wasn't pi, okay? It wasn't the sine of 30 or anything like that. It was just E equals mc squared. But this is the equation that allows us to have energy from the sun. Because what's happening in the sun, billions of times every second, is that 4 hydrogen atoms are combining into a helium atom. And that helium atom has a slightly less mass than the 4 individual hydrogens
Do you want
do.
these?
So what happens then is that mass gets converted into energy. Now, if you consider the speed of light being 3 times 10 to the 8th meters per second, you square that, you get 10 to the 16th. So it doesn't take very much mass at all to generate a tremendous amount of energy. So,
Can I go breathe helium and get energy then?
huh?
Is that all you're saying?
No, no. If you can take hydrogen, smash it together and produce helium, then you can get energy.
In my body?
Yeah, but that's not gonna happen. It takes tremendously high pressure and tremendously high temperatures.
So Jamie, you would probably die doing.
Yeah, it's
But I'd be making history.
true. You wouldn't survive, but you would make history. So, if you look at energy from like a historical perspective, right? So, if you look at like the transformations that like I've seen in my lifetime. So, if you go back to like my dad was born in 1927 at a little farm that was out by Cheney, Kansas. And it was actually up by the lake. And when Dad was little, when they would come into town, they would hook up the horse to the wagon, and they'd leave in the morning, and 21st Street was a set of wagon roads. That's all 21st Street was a set of wagon roads. And they'd come into town, get whatever supplies they needed, then go back. And that was a day trip, okay? Just to go from Cheney into Wichita, okay? So that was late 1920s, early 1930s. So that's how my dad started his view of the world in terms of transportation. Oh, you hooked up a horse to a wagon, that's how you moved. But by the time Dad passed away in 1996, he had seen a huge transformation in how people move. So Dad went from seeing a horse-drawn wagon to being able to get on a plane and fly across the Atlantic Ocean to seeing Neil Armstrong walk on the moon. So my dad's generation saw a tremendous change in how people move, from a horse-drawn wagon to seeing Neil Armstrong walk on the moon. Okay, so that was a huge change.
I thought they had cars in the 1920s.
They did, but they weren't very. They did, but it wasn't
Not in
very.
Kansas.
They were pretty rare. Okay.
Are there cell phones?
Well, really?
In the 1920s?
In the 90s,
Like,
Yeah, there was.
early
They were like
90s, they
really
just started to come out.
Yeah.
Okay, they just started.
It was like the ones with like the antenna that you pull out and all that, right?
Oh yeah, it was the bag phone, and because the batteries weren't very good.
And
Okay.
it was like this tall and like this wide.
Oh, yeah, it was-
And it had like the little dial on it.
Oh, yeah. Now, we'll get to that. So if you look at my generation, okay, my generation has seen a tremendous change in communication. So when I was little, and you all would flip out at this concept, okay, you would absolutely flip out. So we had a phone in the house, and number one, it was connected to the wall, okay, there was no cell phones or
We had one in my
portable
old
phones.
house.
You were tied to the wall.
Landline.
And we had what was called a party line. So on the party line, what you do is you would pick up the phone, and you had 4 or 5 houses that were also on that same line. So you had to pick up the phone and listen to see if anybody else was already talking on the phone.
Yeah, you couldn't use it.
Yeah, and if it was, you couldn't dial.
Talk about eavesdropping.
Oh, yeah, so yeah, you had to watch what you said, because not only would your family potentially listen in on what you said, you had to be aware, because you had 4 or 5 other people that could pick up the phone and listen in on your conversation as well.
I would
Did you
that
know?
would
So
be
if
so
you
fun.
all, oh,
Stop. I'd love to hear people
you
say.
were like, basically like, ooh, okay, yeah, no texting, nothing, okay? Any conversation you had on the phone, you had to realize that that your neighbors could listen in
It's
on
like
that
that'd be a new
conversation.
There were
form of
multiple lines
entertainment.
in a house too, right?
Probably was.
That would actually
Yeah.
be so fun. So
Yeah.
I would love to hear more of those things.
Did y'all like imagine like having your crush live next door and you're like on the phone just
Start my own
like,
gossip
about her?
magazine.
Yeah.
Go like to one of the popular.
Oh, yeah, it was a whole different dynamic. You all, oh, I've got to have my private privacy, whatever.
A guy
So-
call your house phone.
And to
And
dial,
all your neighbors, your
and to
friends.
dial, it was the old rotary dial. Where you had to like put your finger in, like if you would have dialed 3, you put your finger in 3,
Calling to see if I could
push that around, and then it go back, okay? If you went to 9, you go,
Who is this?
okay? So you had to have the numbers memorized, because it wasn't like, oh, I'll just hit, I'll tell Siri to call such and such. Like you had to know the number, okay? So I remember 4th grade. Buddy of mine, Mike Denny. Mike Denny's family got the first push-button phone, okay, where you didn't have to do the rotary dial.
I
You
know,
like
he was
push
the
the
coolest
button.
kid in school.
And we ran over to his house after school just to see the push-button phone, because that was like cutting-edge technology.
Were they rich?
Not bad, but his dad was a bit of a techie, okay? And they were also the first ones to have the first video game. Anybody know the first video game? Pong, okay? They had Pong. And if you've never seen Pong, it was like tennis, and you had a knob and you would slide this, like, the paddle up and down and you would make the ball bounce around, okay? So that was like the coolest thing ever. It's like, oh, it's a video game, whoa! And so like, even like my junior year in high school, okay, you had to do your junior research paper. And
The library.
yeah, you were in the library. You wanted to quote something. You had to either physically get the book. If you wanted out of a magazine, you had to like hopefully the library
Screw
had.
that. You
Huh?
could not cheat on homework back then, could you?
It was tougher. Let's put it that way. Okay.
Are you basically saying
Why
that
is
you
that
did
the
it?
first thing that you think of?
It just. But like so, if you
He said
wanted like
English
a
paper,
quote,
looking up
you
at
had to
looking up
like
paper.
write it down, okay? And if the school didn't have the magazine, you might have to like go to the Wichita Public Library because they had like a.
How would you even know about a magazine?
Huh?
How would you even know about a magazine?
It was like what was called like the Dewey Decimal System. You had like a book of.
I remember
You
that.
could go through and you could like. It was sort. You had a published copy of the topics and what magazines you could find them in. Yeah. And then you actually had to like type the paper, okay? There was no like cut and paste, oh, I'll just take this and I'll insert it here, right? Like you had to physically type the paper. And so now you look at your phones, okay? Your generation has more access to more information than any other generation that has ever lived on this earth,
Yeah.
okay? Seriously, you don't even have to like type anything in, you can just talk to your phone, you know?
I have Siri off because she freaks me out.
Okay, well, but I'm just saying it's
I have
an
it on
option.
phone.
So you might not know what to do with the information, but your generation can access more information than any other generation that's ever been on this earth. So that comes with a certain amount of responsibility. So I think here's what's going to define your generation, and that's oddly enough going to be energy, okay? Because with this, you all were more dependent upon energy than any other generation that's ever existed, okay? Imagine, if you will, the internet goes down, okay? The internet goes down. You guys have nothing. You have no social media, nothing, okay? Can't text,
I would
can't
like it,
call.
yeah, I would
Just
like
go
it
outside.
That'd be so much better.
You can go outside and get some fresh air.
Okay, but I'm just telling you, think about how your life would change. Think about even if you look at electrical potential energy, the ability for your phone to store energy. Imagine if cell phones only worked if they were plugged into a wall.
I love
We'd
it.
all be a
I
little
love
better
it
off.
so much.
So yeah, you would have the prime spot, okay? Because you could plug your phone in. You in the middle, you'd be like, oh, can I get an extension cord, Mr. Burkhead? Come on, you know? Even look at how your car starts. What's the function of your battery in your car?
It holds the power to start your phone.
Store energy, right? Anybody know how the first generations of cars started?
No.
There was a
Hardwired.
crank. So you pull this crank out and you put it in the front of the engine and you would manually turn that crank.
Oh,
And that's how you would start your
They
car.
should add that in case my battery dies again.
Well, there's so many electronics.
There's too much.
now. Yeah, it is just, jump started.
Yeah,
So-
I've gotten stuck too many places. My battery sucks.
But here's the deal. We as a society have become very, very, very dependent upon a readily supply of cheap energy, whether that's gasoline, whether that's electricity, whatever
See,
that
gas
is.
is cheap.
Gas.
Now, well, relatively.
Heck no.
So, when you look
Have you seen
at,
California's?
well, former senior mines in New Zealand, they're paying the equivalent of like $10 a gallon.
Stop.
No, seriously.
It's a preventative to get people to start walking.
Seriously, she just posted on Facebook the other day, in New Zealand, gas, if you do the exchange rate, it's like $10 a gallon.
I would never drive.
It's good for the
So,
environment.
no, but seriously, think about how your life would change if gasoline goes to $10 a
I'm gonna
gallon.
ride the bus.
Yeah, well, guess what? Hey, riding the bus isn't so bad.
Transportation is
Hey,
good.
that bicycle, let's dust that off, okay? Hey, saddle up the horse, let's go trigger, all right? So, your life would change.
It probably costs money to ride the bus, because the school would take you so much gas.
Yeah, no,
Oh, yeah.
transportation.
Oh, yeah, it would.
I'd be walking.
But here's
No,
the
they
other
would just
thing.
run the bus.
Here's the downfall. Okay, and this is kind of my whole emphasis in terms of like the solar project, is that unfortunately how we're used to producing energy, burning coal, burning gasoline, whatever, natural gas, that emits carbon dioxide. So if you look at kind of like the worst case scenarios, and you cannot dispute the fact that carbon dioxide levels it's like a J curve, okay, it's this huge spike in carbon dioxide levels since the Industrial Revolution. And if you look at temperatures have gone up. So that was kind of my thing when I started the solar project. Like, okay, we can't continue to produce electricity the way we've always done it. And when we've always done it, it was like we take coal out of the ground, which is carbon dioxide and fuel intensive. We ship it on a train, we burn it, that emits even more carbon dioxide. We heat up water, the water turns into steam, the steam spins a turbine, that generates electricity, we ship the electricity 200 miles, and I can make toast, okay? And any electricity story ends with, we can make toast, okay?
You believe in global warming?
Oh, very much so,
What do you mean? There's no such thing as not believing in it. It's just true.
yeah.
Or like, do you believe it's like,
Man-made, related to carbon dioxide levels, emphatically yes. Okay, emphatically yes. Now,
It's just true.
I
so,
was asking if you think it's like just the Earth doing it by itself or like us?
No, it's
No,
us.
it's us.
It's us.
it's us. Carbon dioxide has a unique capacity to let sunlight in, but it traps the infrared radiation that's emitted back. So, Kyle,
How long do you have to go be until it's actually a problem?
depends on where you, if you're living in some South Pacific islands right now, it's a problem right now. If you live on some coast along Alaska, it's a problem now because your villages are going underwater. So, is it gonna be a problem here in Kansas? Probably not for a while. So it really won't
It's
be
gonna get hot.
relevant to
It's
us.
gonna get.
How long is a while?
It depends on the computer model.
Your kids are gonna have a problem.
But it isn't so much us, but it becomes more of a global issue. You're gonna have regions, depending on which computer model you look at, you're gonna have regions in the world where it will become so hot that you cannot live there. I mean, like portions of the Middle East, portions of even the southwest part of the United States. What are you gonna do with millions of people that live in regions where it is so hot it is unsafe to live there?
Kill them.
What?
Mason, he's
Hunger Games.
I'm hearing
Hunger
Think
Games.
before you talk?
Still all.
No. The answer is no, Bruce.
Okay, seriously, just don't.
That's like
So,
twisted version of
that-
natural selection.
The climate part might not impact us, but if you look at what's that gonna do to the world economy, if you look at what's that gonna do to the migration of people, okay? What are you gonna do with people? We can't shoot them, okay?
Let them fend for themselves.
Okay? But seriously, but it is gonna impact Kansas in terms of what crops we're gonna grow, in terms of the length of the growing season. So it might not, are we have to worry about flooding here?
Yeah, I was gonna ask, how long before like there's no more land to live on?
That would be
Well,
a huge
there's a cap
stretch.
at how many people
Okay.
can live, so that's never really gonna happen.
Or what it's habitable for? You know, in like years.
We don't have enough
I
food
can't
for that
even
even to
begin
happen.
to guess.
We don't have.
Because the good news is we can control it,
Chill out.
okay?
I say a couple hundred.
We have some control over that. But here's my point that I think is gonna challenge your generation without carbon dioxide emissions. Because you have to have the electricity, you have to have the energy.
Make a little mini sun.
Well, that actually has potential. So one of the things you talk about is basically a miniature fusion nuclear reactor. Because right now, all nuclear reactors work on what's called a fission process, where you have large unstable nuclei, typically uranium-238, and it splits, and that releases energy, and that heats up water, and you can make toast. So what happens with the fusion process is that the problem is it takes incredibly high temperatures and incredibly high pressures.
That's what my constant.
Oh my.
So what happens in the fusion process is that you take hydrogen under extremely high pressure and extremely high temperature, you fuse those together. The cool thing about it is that your only byproduct is helium gas. Okay? It's like, great, we get to talk funny. That's kind of cool, right? But the problem is that your energy input right now is bigger than the energy that you get out of it because it takes such high temperatures and such high pressure. Theoretically, there's a whole bunch of people that have invested a lot of money into that process. So hopefully in your lifetime, you can see fusion reactors that then you don't have to worry about. It's like there will be no carbon dioxide emissions to produce electricity. We're going to have helium emissions. Okay, that's a problem. Great, we can fill up balloons. That's kind of cool, right? But that's what's happening in the sun. So hopefully, like I said, in your lifetime, you see a transformation in how energy is produced, okay? Whether it's solar, and that's the beauty of solar panels, like, okay, here we have 720 solar panels out here. It generates electricity right there. We ship it 100 yards, I can make toast, okay? Without wasting any water, without burning any carbon dioxide fuels. It's just, boom, here it is. Produce electricity. There's no moving parts. The panels last for like 25 years, okay? And so it's a home run deal. And so that was kind of my push to get the district to try and do something like that. Okay, so let's chit chat. Oh, come back here. All right, so we've got the energy thing. That's working. It is. So if you look at how energy can take on different forms, all right? So got the ball. If I'm going to throw this to Kyle, okay? Am I going to do work in throwing the ball to Kyle? Yes. I'm going to exert a force over a distance, right? And I'm going to change the kinetic energy of the ball. You ready?
Yeah.
Okay? Now, did Kyle do work in catching the ball?
Yes.
Yes. Why?
That's the slow down.
Yeah. Yeah, you exerted the force over a distance, right? Okay? So I did work to increase the kinetic energy. Kyle did work to decrease the kinetic energy. Now, go back. Now, if I don't catch it, okay? If I don't catch it, does the kinetic energy change?
Sort of.
Well,
When it hits the ground.
when it hits the ground. But there's a force that's being exerted on you. But here's the idea. Just like if you don't exert a force, you don't change the momentum. If you don't exert a force, you don't change the kinetic energy. So what we're going to assume initially is that the mass is going to remain constant. The only thing we can do is change the energy, change the velocity aspect of it. What?
For this whole thing.
Okay,
Let me get some of that.
okay.
Where are you going to put it?
Just get it.
Oh.
Jeez.
What's the black letters up there?
That's how far you have to go to still reach the panel. So
108.
you have to knock that down to,
108.
what was it at?
112.
Yeah. How about 107?
I'm sorry.
Oh my God.
Okay.
She was so confident, she said it like 3 times too.
So confident in it.
And it was so wrong. I wasn't gonna say anything, okay? I heard it, that's just like, she'll figure it
I
out.
said it twice.
I know.
I was like,
And I was just gonna go, it'll figure it out, wait for it, okay?
And it's on recording.
This
too.
thing has been going the whole time.
Hey, at least it's not as bad
Okay, we'll stop that. Stand up, right? And I'm gonna lift this thing up. So when I lift it up, do I do work?
Yes.
Yes, why?
Apply force and-
I apply force over distance. Now, by doing that, what type of energy did I store?
Potential.
Oh, right? Because it has the capacity to fall. So if I do work, because it's not gonna swing up here by itself, because Mother Nature doesn't like gravitational potential energy. Because as soon as I let go of it, what's it gonna do? It's gonna change into kinetic, right? So I can lift it up here and store a certain amount of potential energy, like on an arc. I can also just lift it straight up, okay?
Should do that.
In both situations, the change in the gravitational potential energy is going to be the same. Whether I lift it up in an arc or whether I just lift it up like this. So if you think about this in terms of energy being conserved, in both situations, let's say that I store 1 joule of energy. So if I just drop it, that 1 joule of energy is immediately going to change into kinetic energy, right? If I hold it up here and let go of it, I still have 1 joule of energy, right? So no matter the path, when it gets to the bottom, if I store 1 joule of energy here, it's going to have 1 joule of kinetic energy down here at the bottom. Now, we just said kinetic energy was a scalar quantity because it can't be negative. So whether it has 1 joule of energy going straight down or 1 joule of kinetic energy going horizontally, it's still the same amount of kinetic energy. It's just whether is it going straight down or is it going in an arc like this. So it's kind of like Katie Shear is going to go to New York City to see her sister. So one option is that Katie just drives straight to New York City. Okay, great. That's one path that she can take. She might fly to Atlanta, catch a flight in Atlanta, then go to New York City. She might fly to Miami, okay, might fly to Denver. But no matter what, she's going to end up in New York City. So the same thing is going to happen here. If I lift this up, I'm going to store a certain amount of potential energy. The path that it takes to get to the bottom doesn't matter. It's still going to be the same amount of energy. Now, if I take this and hold this up like this,
Oh
okay,
my gosh.
and let go of it.
it won't hit him.
Now,
Moved.
how do I know it's not going to hit me?
Because it's,
It just hit you.
No.
because
Thank God.
it loses some of its energy every time it goes.
Yeah, because
Measures the problem.
yes, like bam, wham. This is just your teeth long now. So, as that came up, right, I only had a certain amount of energy, so it couldn't swing any higher than what the energy that I gave. Now, if I pushed it, that's a whole other story, because then it would have come back. But if I just drop it, it's not going to happen. Now, eventually, short of the string not breaking, if the string hadn't broken, what was that gonna do?
Just stop. Sit at rest.
It's just going to stop, right? It's going to come to rest. So the cool philosophical part of energy is that energy has to be conserved. And you're just changing the form of the energy. So if you look at the movie Monsters, Inc. Okay, what was the idea of Monsters, Inc.?
Scare kids.
Why?
To produce their screams
You,
and collect it.
and collect the energy from the screams, right? Okay, that was the whole idea of Monsters, Inc. So if you look at the process of you hearing me say the word energy, it actually starts with the sun. Sun shines, crops grow, I have breakfast. My body has energy, I decide, hey, I'm going to talk about energy today, as opposed to momentum. I'm going to talk about energy. So my brain formulates this idea that says, okay, we need to talk about energy. So my vocal cords produce a certain vibration, and I send out a series of compression waves in the air that vibrates. Your eardrums pick that vibration up. Your eardrum vibrates, sends that message through the bones of your inner ear to your auditory nerve. Your auditory nerves sends that signal to your brain. Your brain processes that and goes, oh, Brooking's talking about energy, okay, as opposed to momentum.
Too complicated, you speak, I hear, that's it.
Yeah, let's go with that, okay? But out of all that energy, when I say the word energy, only a certain amount of it goes to making your eardrums vibrate. Most of that energy is still in the room, but not as anything that's functional. So they've done the math, and somebody was really bored, that if you scream, ah, like that for like 8 hours, okay? And if you can harvest that energy, you can make a pot of coffee. Okay?
Wow.
Yeah, like I said, somebody was really
You're gonna
bored.
need coffee.
Burton, if you're a
In
coffee
Monsters
maker,
Inc., laughing actually gives more energy.
I said you.
Oh, yeah. But, so here's the philosophical part of this. So, I've taught in this room since 1996. So, all the noise, all the laughter, all the tears, and there's been some, that, I'm not gonna lie, okay? I would bet.
How have you made kids cry?
Getting a bad
you have
grade.
no idea.
They cry.
So, not intentionally,
Make me cry.
but, no. It's not worth the effort. So, but, you know, Bailey Dobler, Bailey graduated maybe 5-6 years ago, and she sat right over there. And she was just, Bailey Dobler was just stressed out. And she was crying, and she goes, and it was funny, she goes, Mr. Urquhart, what's the terminal velocity of a tear running down a physics student's face? And it was like, I don't know, Dobler. And she had like, I've still got the picture, she sent me a picture of like her homework assignment with like this wet spots from
There was a tear on my homework assignment.
You can relate? Okay, yeah. So, I've still got that picture on my phone. So, anyway.
Morning problem.
So, but if you could like harvest that energy, okay, and do something with that, then you can make it into, you know, like look at all the noise that happens in the commons during lunch. Okay, wow,
Can we
there's
make a
all
pot
that
of coffee
energy.
with that noise?
But the huh?
Can we make a pot of coffee with that noise?
Well, the problem is that how do you take that diverse energy and use it back into something that you can use? Okay. Now, even if you look at like earthquakes, right? Anybody, I'm guessing you all been in Kansas, right, have felt the earthquakes, okay? And that wasn't something that anyone ever experienced in Kansas. And,
It started happening everywhere. Like,
yeah,
it
so
didn't-
I remember the first time it happened. It was a Saturday night. K-State was playing Oklahoma State in football. I was laying on the couch watching it, and like the whole house shook. And it was like, called my brother. He lives like a mile away. Said, "Scott, was this just me?" He goes, "No, I felt it too." It was like really
San
weird.
Andreas Fault
Okay?
gonna come and get us.
Huh?
San Andreas Fault gonna come and get us.
No, that's not the same. So, but here's the point: is that if you look at what an earthquake is nothing more than taking potential energy and changing it into kinetic energy. And that energy is stored in the fault lines. You look at a big idea, you look at a planet in an elliptical orbit around the sun. Does the kinetic energy of that planet change?
Yes.
Yes. When does it have its most kinetic energy?
It's closest.
When it's closest, because this is when you have your highest velocity, so you have your highest kinetic energy. Out here, you're storing potential energy because it's further away. So, some people like a container analogy. So if you look at me taking this rubber stopper and lifting it up, okay, hey, I store a certain amount of potential energy. Maybe I make it swing on an arc or something like this. So I store a certain amount of UG. And this is your kinetic energy container. So if I pull this up, I store UG, but as soon as I let go of it, what happens to that potential energy? Changes into kinetic. So imagine that there's like a siphon that allows this energy to move from one container to the other. So as this energy level goes down, that kinetic energy level goes up. So is it possible for an object to have both kinetic energy and gravitational potential energy at the same time.
Yeah.
Yeah, what has to happen?
Has to be moving up.
Go,
Yeah, it just has to be moving above the ground, right? So if I throw this rubber stopper to Kyle, it's going to have kinetic energy because it's moving, and it's going to have gravitational potential energy because it's above the ground. Okay, so yeah, you can have both at the same time. But if I just hold it up here, I only have what? Yeah, I only have UG, okay? But if I drop it, then it has UG and kinetic. Okay. So if you look at, let's say you have a 10 kilogram car that's at rest. So Hannah, pick a number between 10 and 20.
8.
Huh?
8.
Between 10 and 20.
Oh,
Wow.
sorry.
Hey, don't have her say any more numbers.
I can't be 8.
I was completely spaced.
If she's nothing.
No, like, no.
We could go with 8 if you really hung up on that
Why
number,
can't
okay?
it just be 8? Why does it be between 10 and 20?
Please tell me
so
the camera
wrong.
isn't rolling.
Oh, it is. So,
14.
14. Okay. So the final velocity of the car is 14 meters per second. Okay? All right? So, did the kinetic energy of the car change?
Yeah.
Yes. Okay, we went from rest up to 14, right? So, is work going to be done on the car?
Yeah.
Why? How do you know? How do you know work's going to be done? Page the rage. How do you know work is going to be done on the car?
We have a force,
How do you know that there's going to be a force acting on it?
because it's moving.
It's accelerating.
Yeah, it's accelerating. We're starting from rest and we're speeding it up, right? Okay? So, we're going to do work, which is going to be force times distance, right? Now, that's going to equal the change in the translational kinetic energy. Now, the other thing that you'll see in this unit is that it's very possible to get the same answer 2 or 3 times in a row, okay? So like the work is going to equal the change in the kinetic energy, which is going to equal force times distance. And that change in kinetic energy, you can write it as kT minus kT naught, your final kinetic energy minus your initial kinetic energy. You can write that as 1/2 mv squared minus 1/2 mv naught squared. And if you really want to get fancy, you can factor out a 1/2 m and have that as v squared minus v naught squared. So your work could equal your change in the kinetic energy. And if your initial kinetic energy is 0, that's also going to equal your final kinetic energy. So you might have 3 answers that are the exact same thing. Okay? And that's going to happen. And don't flip out and go, oh my God, I had the same answer. It's okay, because it equals so many different things. Okay, so in this situation, I know the initial kinetic energy of the car is 0 because it's at rest. Okay, so it has no initial kinetic energy. So I can find my final kinetic energy. So somebody get a calculator. So we're going to take 1/2 times 10 kilograms times 14 meters per second, not 8, okay, squared. So let me know what you get out of that.
980.
980 joules, okay? So that's my final kinetic energy, right? Because I didn't have any to start with. Now, because velocity is squared, if I had doubled that velocity, what would that do to the kinetic energy? By how much? Factor of 4. Because of the fact that that's squared. So if you go twice as fast, your kinetic energy goes up by a factor of 4. But if you double the mass, what happens to the kinetic energy? Then it just doubles, because that's just mass, okay? So if you double the velocity, kinetic energy goes up by a factor of 4. Double the mass, it just doubles up. So that's my final kinetic energy. So now I can find my change in my kinetic energy, which is going to be 980 joules minus 0. Oh, I still get 980 joules. Now, the work is going to equal my change in kinetic energy which is the exact same thing of 980 joules. So my final kinetic energy is 980 joules. My change in kinetic energy is 980 joules. The work is 980 joules, okay? Now, at this point, I don't have enough information to calculate the force because I don't know the distance. So, page the rage. Pick a number between 2 and 10.
8.
8. I knew that was going to happen. So, let's say that this car travels 8 meters while this is taking place, okay? That's about 8 steps, all right? So, since it takes 8 meters, now I can calculate the force, because work equals force times distance. So if my work is 980 joules, and it travels 8 meters, so somebody take 980 and divide that by 8.
$122.5.
122.5? So call it 123 joules. Oh, excuse me, newtons. Newtons, okay? Now, here's how you can represent this graphically. If you were to draw a force distance graph, what we're saying is that we're exerting 123 Newton force over a distance of 8 meters, which is going to create 980 joules of work, which is going to create that 980 joules of change in the kinetic energy. Now, let's say Paige, instead of picking 8 meters, let's say Paige had picked 4 meters, okay? If she had picked 4 meters, and listen very carefully before you answer this, if she had picked 4 meters, what would that have done to my change in my kinetic energy?
Nothing.
Absolutely nothing, right? Because the car is still going from 0 to 14 meters per second, okay? What is vital here is that you keep track of what you're holding constant and what you're changing, okay? So there's still going to be 980 joules of work done. There's still going to have a 980 joule change in the kinetic energy. But what's that going to do to the force? Right, because now instead of dividing by 8 meters, I'm going to divide by 4 meters. So graphically, what that means is this. I'm going to have twice the force, but that's going to be exerted over half the distance. But I'm still going to have the same area, because I'm still going to have the same amount of change in the kinetic energy. So I can either have a small force exerted over a larger distance, or I could have a bigger force exerted over a smaller distance. And that's the decision that you all make whenever you hit the brakes in your car. Oh, you're driving 40 miles per hour. Brakes, yeah, do you slam on the brakes, or do you just kind of or do you let the car just kind of coast to a stop? Okay? No matter what, it's going to be the same change in the kinetic energy. Your car is going to go from 40 miles per hour to 0. You decide the rate at which that kinetic energy changes. Do you slam on the brakes? Do you let it go? Same thing is true if you're speeding up. Okay? If you're speeding up, wow, you run up on the gas, right? Okay? And you get this rapid change in the kinetic energy. Or do you take a more gradual approach and slowly increase up to 40 miles per hour? So fundamentally, when you drive, you're deciding the rate at which your kinetic energy changes. Okay? Got it? Good? Okay, so stop that. So let me go over a couple of things on this assignment. So when you get to question number 9 about a tennis ball hitting the floor, okay, the great dissipator of energy is thermal energy, okay? So, like, you know, if you take a golf ball and you let it bounce, okay, hey, it's not going to keep bouncing back up to that same height. You're going to lose some energy in the collisions. You're going to lose some in making sound, okay? So the great dissipator of energy is always heat and thermal energy. When you get to question number 13 with the tennis ball, you're going to have to go old school. Either you can use F equals ma find the acceleration, and then use v equals v naught plus at. Or you can look at it from change in momentum equals force times time equals m delta v. So 13, you got to go old school to find the velocity before you can find the kinetic energy. Okay? When you get to number 14, that's a situation where you might find you have the same answer again and again and again. Because on 14, you're finding the work, then you're finding the change in the kinetic energy, and then you're finding the final kinetic energy. So particularly on a question like 14, there might not be any calculations to do, but you're going to have the same answer like again and again and again. Okay, other than that, you're on your own. So stop that camera for the last time.